In this module, we are going to talk about EIGRP metrics, the composite metric, and some of the other metrics that EIGRP might use in some circumstances, and the best path selection process in EIGRP. But this is not going to be so simple and straightforward as you might expect. We are first going to talk about routing information exchange, or how do EIGRP routers actually exchange the information about the routing tables. What are the EIGRP metrics? What are the components? How is the final metric that is used in the routing table calculated and determined? Then we are going to examine what are the internal databases in use by EIGRP, and here we are going to look at the topology database and obviously the best path selection process that happens there. And obviously here we are going to look at how the certain router locally makes this determination, what is the best route, and if it cannot make a local determination about the best route, how it might ask other devices in the network about what the best path to reach certain destination is. And finally, we are going to talk about equal and unequal cost load sharing as supported by EIGRP. EIGRP routing information exchange is a process that begins as soon as neighbors have discovered each other and they have some route that they need to communicate to each other. This process is accomplished and completed using separate packets, separate type of EIGRP packets called update and acknowledgement packets. Now, I should really point out that treating the acknowledgement packet as a separate packet type is really just a minor logical concept, because the acknowledgement packets are really just unicast hello messages that are sent by the recipient of the information to the sender of the information. But let's take one step back. The update packet is a separate packet type, and it contains information about the routes that EIGRP router needs to communicate to its neighbor. Once this information has been compiled, once the router knows what it's going to tell its neighbors, it's going to send this update information, it's going to send the route to the neighbor, and it's going to expect the acknowledgement of this packet. As I say, this acknowledgement comes in a form of a unicast hello. But what about the actual update? Is the update unicast or is it multicast? That depends on the interface type on which you have this configured. If the interface type that you are using is, for example, Ethernet that supports multiple neighbors, the actual update packet will be sent to 224.0.0.10, which is the multicast destination used by pretty much all EIGRP communications, and then every single neighbor will need to acknowledge this packet separately. If we don't get an acknowledgement from a particular neighbor in a certain period of time, non-configurable period of time, in that case, we are going to send a unicast update to that neighbor and expect the response. If we don't get it, we are going to declare that there is something wrong with this neighborship. Now, this operation that I just described is something that EIGRP calls a reliable multicast delivery. This is a process that always happens in EIGRP information exchange, but you as a network engineer, as the end user of the equipment, really have no way to influence how this process happens or modify these timers. These timers are actually dynamically calculated and determined by each individual device. But while I'm on a subject of talking about EIGRP packet types, let me just mention that there are overall 5 packet types if we treat an acknowledgement packet as a separate packet type. They are the hello, the update, the acknowledgement, the query and reply packets. I'm going to talk about the query and reply a little bit later on. But taking even one more step back here, there are 2 kinds of updates that EIGRP can send. This is the full update of routes, and this usually happens when the neighbors have first discovered each other. When this happens, when the neighbors first discover each other on a particular network segment, they are going to exchange all the information about all the routes. The good news about EIGRP is that this really happens only once. There is no periodic information exchange. There is no periodic reflooding of this information. This information is going to be valid as long as the neighbors exist, or one of the neighbors decides that information that it sent previously is no longer valid, and it's going to send a new update. For all the changes that happen after this initial flood of information has happened, after this initial large update has gone out, are simply going to be partial updates when the metrics on particular routes change, or if the new routes have been added or being removed from our routing tables. Let's now take a look at this process in some more detail. So let's say that I had two routers, R1 and R2, that are interconnected on, let's say, their gigabit interfaces 1, and that the network between them was 192.168.12.0/24. And let's say that on R1, say, we had a loopback interface 192.168.01/32. So when we configure EIGRP to run between them, and let's say that we are going to configure EIGRP process, let's say 12, to run between them, what we expect to see here is R1 and R2 to send each other periodic hellos. So if I enable my EIGRP only on the gigabit interfaces, the only communication that I'm expecting to see are going to be EIGRP hellos. But let's say that now I add my loopback interface to the EIGRP configuration. What's going to happen is R1 is immediately going to communicate this information to R2. So this is going to be the update message. And once R2 has received and processed this update message, what it's going to do, it's going to send back the acknowledgement to R1. So this is the relevant part that happens here. There is going to be an additional process that's going to happen, and that's going to be that R2 is going to inform R1 that it has this new route, but it's going to send it with an unreachable, infinite metric back to R1, simply telling R1, hey, I have this route, but it's not really reachable through me because I have received it from you. And R1 will also send the acknowledgement back to R2. So let's now take a look at this in action. I'm going to start by simply building this network that I just described. I have already configured layer 2 part of it, so I do have the connectivity between R1 and R2. So let's just go ahead and confirm that. On R1, I'm going to say show IP route connected, and what I'm looking for here is the network 192.168.12.1. And I do have this network. Actually 192.168.12.0, but I do have the locally attached interface there as well. So I can ping router 2, and on R2, show IP route connected shows me again that I do have my 12 network there, and I can ping R1. So let's go ahead and configure EIGRP here. I'm going to do a very simple configuration of EIGRP. So I'm going to say router EIGRP 12 here, and I'm going to say network 192.168.12.0. I'm not yet going to advertise the loopback interface, because what I want to do is I want to actually start my Wireshark capture and get these update and acknowledgement packets as they are going along, so that I can show you how they actually look. And on R2, what I'm going to do now is I'm going to say router EIGRP 12 network 192.168.12.0. So at this moment, I can go ahead and start my Wireshark capture here, and I'm just going to capture this on Ethernet 1 interface here, and what I'm interested in seeing are only EIGRP packets. And I can see here that the hellos are being sent from time to time. Let's go back and add that loopback interface to our EIGRP. And I'm obviously going to do that on R1. So I'm simply going to repeat this command here, and I'm just going to make sure that I add the loopback interface here, and I'm quickly going to switch. When I press enter here, I'm quickly going to switch to my Wireshark, and now I'm going to stop the capture so that I can explore what was happening here. Now, what I'm looking for here is this update packet here. So I have received the update packet, and I want to observe couple of things here. Now, the first thing that I want to observe is that the source IP address of the packet was obviously R1, and I can see that the destination was 224.00.10. So I can see that this was actually a multicast update. Now, if I open and take a look at what is contained in my EIGRP update packet here, what I'm seeing is obviously that there was an internal route that is being advertised, and I can see here the network of my loopback interface 192.168.0.1/32. And here, if I open this field that talks about wide metrics, here I will see information about the reliability, load, delay, bandwidth, and so on, about the things that are actually used to calculate the metric. And I'm going to talk about these metric components later on. So I can see that there was this update packet going out. And as I said, please take note that the destination of this packet was 224.00.10. Now, the next packet here that we are seeing is an actual acknowledgement. And you can see here that Wireshark tells us that this was a hello packet, but it's actually an acknowledgement packet. So this bit here tells us it was an acknowledgement, or actually this bit if we were using Wireshark to analyze this, but I'll show you where in the packet this is actually contained. Now, the more important information here is that the source and destination are that of R2 and R1 respectively. So here we have R2 is sending the packet as unicast to R1. These are no longer multicast packets. So even though the update here was multicast, the confirmation that this was received is sent as unicast. The reason for that is, remember that this is an Ethernet interface. We could have multiple neighbors, and R2 is telling R1, hey, I received this information. There is no need for R2 to tell this to some R17 that might exist on the same subnet. So it just informs R1 about this information. Now, if we go back to our update packet here, there is going to be a field called sequence, and we can see here that sequence was 3. What is the sequence number going to be? It's not really relevant, but what is important that in our acknowledgement packet here, we're going to have the acknowledge field with the same number 3. So this here tells us that, look, I am acknowledging right now I'm acknowledging the arrival. I'm acknowledging that I have received the update that carried the sequence number 3. Now, another thing that I mentioned before is that we can see that R2 here is actually going to update as well. It's going to send the information about this same route. We can see that this is the same route we are talking about. Actually, not that one, that's the route already. It's this one here. We can see that the same route is being sent, and we can see here that the delay has been set to infinity. So we are basically advertising the route back to R1, and we can see that R1 is actually going to confirm, yep, I have received this information. I'm not going to do anything with it, but I have received it. So in a nutshell, this is how the routes are exchanged between two neighbors. Let's now talk a little bit about EIGRP metrics. The reason why I have an empty slide behind me is that I would like to start this part of this session with a little bit of a warning. That warning is really that what I'm about to say is not necessarily in line with official Cisco documentation, or for that matter, Cisco Press books. There are many misconceptions when it comes to EIGRP metric. The first thing that you are going to hear is people talking about EIGRP metric. This is not necessarily correct. EIGRP has multiple metrics, and what makes up those multiple metrics is also a matter of a debate. Allow me to explain that to some degree. The first thing that I would like to mention is that when you look at the output of certain commands that I'm going to show you in iOS, like for example, show IP EIGRP topology, you're going to see the mention of this concept of this term vector metric. Now, vector metric is simply the list of all metric-related information that is communicated and maintained between the neighbors and in their topology tables. What constitutes vector metric are bandwidth, and only the lowest value of the bandwidth on the entire path is going to be carried along. Delay, which is the cumulative value of all the delays configured on the interfaces along the path. Reliability, and here we are again keeping just the lowest value on the path. Load, and the highest value is kept. Now, the next two are what is a matter of debate. Some people consider these to be part of the metric, some don't. I personally do consider them to be part of the metric, part of the vector metric, and they are MTU, where only the lowest value is carried, and the hop count, which is the cumulative value, and it by default has maximum value of 100. Which means that if we receive the route that has a hop count of say 101, the local router won't use it. It's sort of a last resort loop prevention mechanism. Now, there could be some other reserved values that might be used in the future by EIGRP, so there is a possibility of seeing that in output of some commands, or indeed when you do capture of updates on your interfaces using say Wireshark. Of those values, some values are going to be used to calculate the composite metric using the metric formula. Those values that are going to be used are bandwidth, delay, reliability, and load, and by default only bandwidth and delay are going to be used. Reliability and load are not used. These values are then used in conjunction with the so-called K values, and there are 5 K values, and depending on the iOS version you might actually see K number 6 as well, which is going to be used with those other reserved metrics in some applications that really have nothing to do with routing of IP traffic. They have to do with something else. And these 5 K values, by default, K value 1 and K value 3 are those that are going to have non-zero value. And these are the values that are used to modify bandwidth and delay in some way. K values 2, 4, 5, and 6 for that matter have value 0. So how is this used together with our metric formula? So let's take a look at the metric formula. Wow, this is fun. Now, what I want you to look at here is not something that you can probably or possibly remember. This is a very involved formula. So let's take a look at the important bits. The important bits here are that there is a certain K value number 1, and we can see that the default here is to have it a non-zero value that is related to bandwidth. So we can say that the K value 1 controls how bandwidth will be used to calculate the metric. Then we can see here K value 2, which is again used with the bandwidth, but really what figures here is load. So we can say that K value 2 is used to control how we use load information in calculating our metric. Then we can see a very straightforward relationship between K value 3 and delay. So we can say that K3 here controls the delay. And remember, K1 and K3 are those that are by default set to 1. The others are not going to be used. And then we have K values 5 and 4. So 4 and 5 are actually going to be used to control reliability as part of our metric. Now, no one really expects you to know this formula, to know how to calculate the metrics manually, but it's a good thing to understand how this process actually works internally in iOS. One thing that I would like you to pay very close attention here is that MTU, hop count, and other reserved values by default do not figure in this metric formula here. So MTU, even though it's communicated as part of the vector metric, it's not going to be used when calculating the composite metric. And composite metric is the value that ends up inserted into the routing table. This is what is going to be used to calculate the best paths, to insert them in a routing table, or to find the alternate paths, whatever they might be. So the composite metric is what is actually used to make routing decisions. But in some cases, and some relatively obscure cases, the MTU value can be used as a tiebreaker information. If we have multiple routes that say have equal cost, and we are exceeding the number of routes that can be inserted by EIGRP into into the routing table, we need to make a decision which route to use, which one of those many routes we are going to use. And MTU comes into play here. Those routes with the highest MTU will be inserted first, and then simply then other routes are going to be inserted by their age of arrival. So the youngest routes are actually not going to be used. If they all have the same MTU, then just the age will be used. And as I said, the hop count is going to be used only as the last resort loop prevention mechanism. So let me present you this same information in slightly different way so that you can maybe see the relationship between these metrics. So we have now learned that EIGRP has bandwidth, delay, reliability, load, MTU, and hop count as parts of what I like to call, or what EIGRP calls, vector metric. So this is the information that is always going to be communicated to the neighbor. So all these 6 values will be communicated to the neighbors. Based on the values of these 4, so bandwidth, delay, reliability, and load, we are going to calculate the composite metric. So composite metric is going to be calculated using these 4 values. But these 4 values are not born equal. Bandwidth and delay are, first of all, used by default, so we can say that they are used by default, but also they are something that, and this is my term, I like to call hard metrics. And reliability and load are something that I like to call soft metrics. Now, why do I call them hard metrics and soft metrics? Any change in hard metric, that means whenever we change the bandwidth or delay associated with a particular interface, the change of these values is going to trigger what is called a reconvergence event. Reconvergence event simply means that the router, as the result of changing these values, is actually going to advertise the route associated with this interface. However, change in soft metrics, that means if reliability or load change on an interface, does not itself trigger a reconvergence event. So if the reconvergence event was triggered by change of hard metrics, the snapshot value of reliability and load would be taken at the time of the convergence event and used to advertise the routes. Now, mind you, reconvergence event is also interface coming up or interface going down. That is also a reconvergence event. Now, MTU, as we learned before, is going to be used as a tiebreaker. And hop count is going to be used as the last resort loop prevention. Hop count can also be used for very esoteric, very unusual form of route filtering that we are going to examine a little bit later on. How can it be used? Let's say that we have a network in which we expect the routes to be only, say, 2 or 3 hops away. So no matter where the routes are coming from, let's not accept routes that have more than 4 hops. In that case, we could configure our router to reject all the routes that have 4 or more hops. And in that case, hop count is not only going to be used as a loop prevention mechanism, which it is what it's designed to do, but it's going to be used as a filtering mechanism. Not a very efficient or very scalable or very flexible one, but it can be used as a filtering mechanism. Now that we know what makes up EIGRP metric, let's take a look at how this information propagates throughout our network. So let's say that we had a network consisting of, say, 4 routers, and I'm going to call them R1, R2, R3, and R4. And let's say that here behind our router R4, we had some network, let's call it network N, that we wanted to advertise using EIGRP throughout our network in this direction here. Now, as this information goes from R4 to R3 to R2 to R1, each of the routers is going to modify the vector metric in some aspects and then communicate that information to its neighbor. Now, to examine this, I'm going to give all of these interfaces on my routers some identifiers, some names, so that it becomes easier to understand how this information propagates. So let's say that on R4, this interface here is interface 1, this is interface 2, 3, 4, 5, 6, and 7. Now, each and every one of these interfaces will have associated value of bandwidth, associated value of delay, reliability, load, and MTU. Now, hop count is not associated with any interface in particular. It's simply going to be increasing from R4 to R3 to R2 to R1. So that information is simple enough to understand. Now, when R4 injects this route into EIGRP, it's obviously going to use the information associated with this interface. That means interface associated with bandwidth associated with interface 1, delay, reliability, load, and whatever the MTU was. Now, remember before I proceed that for bandwidth, at the end we are going to be seeing only the lowest value of the bandwidth. For delay, we are going to be seeing the cumulative value. For reliability, we are going to be seeing the lowest value. For load, we are going to be seeing the highest value. And for MTU, we are going to be seeing the lowest value. For hop count, it's also going to be cumulative value here. So when R4 advertises this information now out towards R3, important thing to understand is that this interface 2 will not figure in any way in propagation of the metric. What R3 will do when it receives this information here, when it receives this information from R4, it's going to take a look what is the information that it has received. So all of this information as it was received from R4 to R3, and then it's going to modify these metrics as they are received according to whatever the configuration on interface 3 is. So we can say that so far interfaces 1 and 3 have participated in calculating the metric. Similarly, when R3 advertises this information to R2, interface 4 will not figure in this communication. What will figure is the configuration on interface 5. And again, when R2 communicates this information to R1, whatever was configured on R6 is irrelevant. What is configured on R7 here is relevant. So we can say that interfaces 1, 3, 5, and 7 will be the ones that are going to be taken into account at all to calculate final metric as this route is being advertised from R4 to R3 to R2 and finally to our R1. At this point you might be asking yourself, why is this so? Why are these interfaces here, 2, 4, and 6, not used in calculating the metric? Well, think about it. When the routing information is communicated in this direction, that is done for the purpose of sending the actual traffic in this direction. So if R1 has the traffic to send, is information on R6 in any way relevant to R1, or is it the information on R7 that is actually relevant? Same thing goes for R2, same thing goes for R3, and finally same thing goes for R4. We don't care what is some fictional cost on devices on network, and we care about what is our own cost, what is our own metric to actually send this traffic out of this interface. The time has come now to talk about EIGRP topology database and the best path selection. But as you are probably used to by now, before I can do that, I have to talk about one other thing. And that other thing is a specific EIGRP terminology, specific names for certain things that EIGRP is using that pretty much no other routing protocol does. What are these terms? The first one is a successor. Sometimes this is referred to as simple S. Successor is EIGRP's name for the best route to reach a particular network prefix. So let's say that, for example, we have a network prefix of 192.168.0.0/16, and we have 2 paths to reach it. And let's say that this is the best path, and this is the second best path. This path here simply is called a successor. Feasible successor is a loop-free alternate route And keep in mind that